Guess what it is today? It's question and answer day. So what questions do you have for me from the beginning of chapter 12, sections 1 through 4? What do you want to ask them? Because that's due tomorrow. Yes, ma'am.
22 is 12.3,
12.322.
we're supposed to find that angle of the vertices. I got my angles added up to like over 180.
Okay, so give me the points that are involved in that question.
It's A, 1, 0, -1, B, 3, -0, C is 1, 3, 3.
All right, so for the moment, I'm going to ignore the fact that these are in 3D. I'm just going to label 3 points, right? So tell me, how did you go about finding the angle at A? Because here's my triangle. How do you find this angle?
Okay, well, between A and B.
Ah, those are points. I can't find angles between points. I need vectors. So how do I get vectors here?
You subtract.
Exactly. So what do I subtract from what to get what vector?
B minus A.
Okay, so AB is 2, -2, 1, right? Okay, well, there's one arrow. To get an angle, I need another arrow. What's your next arrow? Here's the problem. If I do AB and BC, when I go to find the angle between those, I have to make a copy of one vector and put it so it has the same terminal point as the other. If I move BC over, BC is here. That angle's not part of my triangle, is it? So what other vector do I need to be able to find the angle with the question mark? Exactly. And that'll help me find this angle, right? But I'm going to need BC. I'm just not going to need it over there. I'm going to need BC to find the angle at B, right? So to find this angle, which I put 2 marks on so I could tell apart, I'm going to need to use BC and AB would point the other direction, wouldn't it? AB would be out here. I'm going to need BA. Fortunately for me, though, how are AB and BA different? So all I have to do is change all the signs, I know BA. And then to do this one, what vectors do I need to use? Exactly. Or you could use minus BC and minus AC, right? But notice how the vectors have either their heads in common or their tails in common. And to find the angle between them, their tails need to be the common point. Yeah, the first thing that happens when I use AB and BC is I get an angle that's not part of my triangle. Yep. I'm going to use exactly that formula. Cosine of theta, well, in this case, I called it question mark, right? So cosine of question mark is AB dot AC over length of AB, length of AC. And then I use the inverse cosine. It says something about like tenths of degrees or degrees or something in the problem. Find to the nearest degree. There we go. Otherwise, I'd say use radians, but I'm safe that way. Nora, thank you, because that catches a lot of people. And it's important to remember that when I'm trying to measure in vectors, they need to originate in the same place. With that same section, problem number 57, which is not one that we were assigned. Problem 57 asks you for the angle between two hydrogen atoms in a methane. And that's a shape that in 3D makes a perfect tetrahedron. And what I'm looking for is the interior angle. So I know from the center up how long it is, from the center out how long. Now, if I can vectorize those things, I can figure out how big this silly thing is. Now, they actually give me the corners, so they show it to me on page 57. Don't know why, but the number 109.4 degrees is stuck in my head when I think about that problem. I don't know if that's right or not, but I think I remember that from chemistry all those years ago. Right. It's that, but I don't remember if that's the interlocking carbon angle for the tetrahedral bonds or if that's the interlocking methane bond. And I think they might be the same, but I don't remember. It's been a long time, but yeah, that's that tetrahedral based structure. And for some reason, that angle is stuck and I don't know why. I'd actually have to do the math. Unfortunately, I can do that. It's this. One of the more interesting pieces of chemistry that was around when I was still a chemist was the development of the structures for room temperature superconductors. And I went to a presentation where they were talking about yttrium, barium, copper oxide as the newest, more high temperature superconductor. I think it was liquid nitrogen temperatures instead of, dry ice temperatures instead of liquid nitrogen temperatures. And so they were like, we can actually do this and it's easy. But I walked in and they had this huge three-dimensional model up on the front of the screen. And I went, I've seen that before. Reach into my bag. It's on the cover of Scientific American. They're like, yeah, well, we're looking at these bond angles and these strengths. And I'm going, that's calculated. So they really did use this stuff. More questions. Has to be more. Yes.
So there was a question number 30 on 12.4. But there's a couple like it.
Find a non-zero vector orthogonal to the plane through the points P, Q, and R. Okay. Let me start with the first question. I don't know what the plane through P, Q, and R is. I don't have any sort of equation for that, but I can think of a plane. Easy way. Here's my plane. I was given 3 points, P, Q, and R, right? 3 dots should define a plane. 3 dots. 3 dots. Okay. How would I find a vector perpendicular to the plane containing those 3 dots? The plane containing those 3 dots is the piece of paper. So I need this vector. How can I find that vector? From just the coordinates of those points. So the cross product is something, right? So the cross product of what? The what is 2 vectors. I need you to take the 3 points and make 2 vectors, just like we did here. And once you've made those 2 vectors, say A, B, and AC, then you'd have a vector, and you just told me the cross product is gonna be perpendicular. So all I would have to do is take the cross product AB cross AC. I think they use PQ and R in that problem. So you could use PQ and PR. You could use QP and QR. You could use RP and RQ. In this case, Nora, you could use PQ and QR. Because PQ and QR will both be on this surface. And then my cross product has to be perpendicular, has to stick out from that surface. So that version of the problem could use any combination of those 3 points to make 2 vectors. No, because think about A, B, and B, C. Aren't they both still on the piece of paper? So their cross product is going to stick out. It'll either stick out point, well, A, B, B, C, it should stick out going in, right? If I did B, C cross A, B, then it would come out. But it would definitely go out of the piece of paper, wouldn't it? So this is really the same triangle idea.
So after you get that vector,
Yes,
you use it to find the area of the triangle.
I don't have to use it to find the area of the triangle. It just says, you said it was problem. Oh yeah, no, what, yes, once I find part B said find the area of the triangle, right? So AB cross AC is perpendicular to AB and AC. Therefore, it is perpendicular to the plane containing them. No, I shouldn't do that. Use words. And then we said that when we did the cross product, it gave us an area. What area did the cross product give us? Bottom of page 817. The area of the parallelogram who has sides AB and AC. So let me draw a quick dirty picture again. Here's A, here's B, here's C. A, B, and AC, I will end up with this parallelogram right here, yes? But I don't want the parallelogram. I want the triangle. How do I get the area of the triangle? So once I have that cross product, I use it to find the area of the parallelogram. The area of the parallelogram is exactly twice the area of the triangle we want. In this case, I would be better off saying I probably want. Would it matter? Wait a minute. If I use AB and BC. Yeah, that's the same parallelogram, isn't it? It's just turned over. So yes, it should work regardless of which two vectors. Okay, I get to ask you this because I know you took the course. If I think of these two vectors as a basis for R2, then I could think of a graph of little parallelograms, right? If I change from using these two to using these two, all I've really done is turned my parallelograms, right? This triangle is now down here. Aren't these two still linearly independent? They're pointing in two different directions, aren't they? There's still a basis for R2. They'll still fill out space. They'll still tile that, and the tiles will be the same size. Go together. I apologize to those of you who haven't taken linear algebra, but that's a sneaky way to think about this. And you'll take linear eventually, maybe. You could also actually show that geometric. Using nothing but geometry proofs about triangle that talking that actually happy to do that. I don't think happy was strong enough of a word. She probably would be thrilled that you would ask this as a geometry question. She loves geometry. More questions, ask me more things. Yes, Ron.
So for 36, which is the kind of volume,
Which section?
oh, sorry. Well, 24,
Okay. Yes.
and it gives you like the edges, so you just like subtract to find those.
Right, because it says use PQ, PR, and PS.
And then when you do the dot product and cross product, does it matter which goes in which position?
No. Okay, so here's the fun part. I'm gonna go back to the picture of that scalar triple product in the book. Because I'm a bad artist, and we just use their picture. Here. Come on, you. Here's their picture, yes? Now, the way they've drawn this, they've used B and C on the floor, and A is coming up. So if we wrote PQ, PR, and PS, we have this thing. But imagine taking those three and turning your fingers. Well, then these two are the floor and this one's sticking up, right? It just turns the shape and turns it physically. So instead of looking at this B and C as the floor, you could look at A and C as the floor. You could look at A and B as the floor, which is just kind of turning your head weird, right? So it really doesn't matter. PQ, PR, PQ cross PR, then dot PS, or is it the other way around? Doesn't matter.
And you put them in like the box for the 9.
In our determinant. Yep. And one number later, presto, I have a volume. Now, the order in which you do them might make this number negative. And if that's the case, it just means that the order in which you did these is kind of left-handed instead of right-handed. So whenever you do this calculation, you take the absolute value of this number that you get out of this process. So really, it doesn't matter which one is which. What matters is their chirality. It's whether you get a positive or a negative as a result. That has effects in physics that are not relevant to the math of the piece for this type of question. It's got results that will come up at the very end of this course, because things that were, quote, left-handed usually mean things out of a system rather than into a system. We'll talk about directionality in 3 dimensions way down the line. So much deep crap there. Better? Yes. Note to self, find calcium. More questions, ask me more things. Oh, Nora, here's how you figure it out. Ah, knew I needed that in my head. Here we go. Let me draw a cube, right? We have I and J and K in one corner of a cube, right? If I do this right, then it should be a 1 for the volume of the cube, yes? But if I do I cross J, then K is going with it. If I do J cross I, then it'd be going the wrong way. So when I multiply by K, it'll end up being negative. See how the order makes a difference to whether I have a plus or a minus? It's not going to change whether it's a 1 or a 0. It's just going to change which direction I thought I would be going. And K is going the wrong way from J cross I. From the right way from I cross J. That's what changes the orientation as to whether it will be a positive number or a negative number. Whether my cross product is in the same direction or in the opposite direction. The third vector that I do the dot product. Now, since I take an absolute value anyway, doesn't matter in the end, but there is a rationale for that handedness. Uh, 12.234. 12.234. That's 12.3. 12.234 is our wind problem, right? The plane and the wind? Yeah. Great. Okay. A wind is blowing from the direction north 45 degrees west. Oh crap, I gotta go all the way back to trig and remember what that means. All right, I've got cardinal directions. Okay. North 45 degrees west means start north and turn 45 degrees to the west. So the wind is on this line, north 45 degrees west. Yes? And it says the wind is coming from that direction. Yes? Yeah. So a vector for the wind would technically point that way. So far, so good. The plane is going north 60 degrees east, start at north, go out to 60 degrees. That way. So the angle looks like it's from the wrong side, right? Because it's coming off of north. And the plane is going that direction, yes? Yeah. So the vector for the plane goes that way. And then I can actually use the speed itself as the magnitude of that vector. So the wind has a magnitude of?
The wind is 50 kilometers per hour.
And the plane?
250.
All right, so at the moment I'm leaving all the units off this piece of paper. I'm okay with that. So the plane goes this way, but the wind pushes it. What's going to happen?
Offset.
So really what I want is to add these two vectors together. And once I've added these two vectors together, I'll know the true course of the plane, and I can even give you its true speed by figuring out the length of that vector, right? But in order to do that the easiest, I should turn these vectors from lengths and angles into components. So here's a question for you. Let's call this the velocity vector for the wind. I want that in components. How do I find that vector?
The absolute value A, absolute value B, cosine theta, is that this one?
That's much harder. That needs two vectors. I only have one at the moment. Let me stick my head back in physics terms for a second. I really want to know how much of this vector goes in the x direction and how much of this vector goes in the y direction. So how do I get the little right triangle pieces?
It's just, is it,
That would give me the pieces. If I knew two of them, I could get the third, but I only know one of them at the moment. Instead of algebra, come up to trig. What trig can I do here? I've got this angle right here. That's the same as that angle. Yes?
yeah,
So that makes this angle negative 45 degrees. So I can say, oh, well, then what I want is 50 cosine negative 45 degrees and 50 sine negative 45 degrees. But notice that I had to change where I was measuring the angle from. Instead of measuring from north, I have to measure from the x-axis. When I go to do that for the velocity of the plane, VP, what angle do I need to use there?
you gotta use the, well, not 60, you gotta take the, you gotta take the, angle from the, like, you gotta subtract the angle from the other two. Like, if that makes sense,
From the other two. I'm not sure I see two others to deal with.
Oh, from the other,
I just need to do that one, right?
yeah.
Well, that makes this a right angle. So
Yeah,
this is
very,
right. So then I can do 250 cosine 30, 250 sine 30. And when I'm done, I'll have the sum VP plus VW. That would be this new vector n. And once you know that vector's length, you can use that and you'll have x and y, won't you? So I can go back and do trig and I can say, oh, if I have x and y, I can get the tangent of the angle. I have x in the length, I can use the cosine of the angle. I have y in the length, I can use the sine of the angle. You can give me the angle, which it says, what is the true direction of the plane? And you can tell me its speed, you know, the length of that vector. This is how wind speed affects flight time. And this is why it's easier to fly from California to New York than it is to fly from New York to California. Because California to New York goes with the jet stream. New York to California goes against it. It's cheaper to fly to London than it is to fly back. That's the way the wind blows. Literally. Which was one of the reasons that the Concorde, as a supersonic plane, was an amazing development. Because by breaking the speed of sound, you break the interaction between the wind and the plane and change the vectors involved substantially. It was one of the reasons for supersonic transport in the first place. It meant that the wind had less of an effect. Less, not none, but much less. Question still? It's cool. This is where the real world comes back to bite me in the ass. Oh,
You verify that they are orthogonal, after becoming orthogonal.
yeah,
How do you do that?
okay. How do you know if two vectors are orthogonal? Means the angle between them is 90 degrees, right? But if I don't actually have the angle, how can I get that information to get me the angle? How are we able to get angles?
Cosine,
And the cosine formula has what? On the top,
dot, oh,
the dot product. And the only way the angle is going to be 90 degrees is if the cosine is cosine of 90 degrees.
yeah.
0. And you just told me the way to get the cosine is to use that dot product. So you're going to end up with this new vector, A cross B, right? And I want you to tell me, is A cross B perpendicular to A? So you take your new vector, A cross B, and you dot it with A. And that should be 0. And then you do the same thing with A cross B dot B. If both of those are 0, then your angle between the cross product and both of those vectors must be 90 degrees.
It doesn't even use like numbers, it's like T cosine T sine T, so.
Yep, that's okay, that's perfectly fine. We're just gonna end up with a lot of things that can't work. So I'll get like T cosine T minus T cosine T at some point. I'll get T sine T, or I'll get cosine times sine minus sine times cosine. Things will, because when I do that, when I do the cross product, I'll end up with a bunch of that stuff, and then I'll do the dot product, and all sorts of stuff should cancel. That idea that I can put variables, T's, into a vector, that's a neat idea. Wonder what that means. Because what's A in that problem?
I plus cosine T J plus sine T K.
I wrote it in component form instead of IJK. Now. That looks complicated. But if you picked a number for T, this would give you some point in three-dimensional space, right? And as T changes, that point's going to change. I've done this before. I did it last semester. But I did it with just 2 of them instead of 3 of them. What did we do when we did cosine T comma sine T? We thought of that as X and Y, didn't we? And we graphed parametric things. This is something parametric in 3D. And the vector is pointing at it, whatever it's doing. It's drawing for me, like an Etch-a-Sketch, but it's got 3 knobs instead of 2. It's got an X knob, a Y knob, and a Z knob. You know, like a 3D printer. The fact that it has letters in it means unfortunately my cross product part is going to be messy. But then my dot product with the eventual result should, everything should cancel out when I'm all said and done, because that dot product should be 0. We'll come back to this one. I like this one. Almost all of the concepts we start with numerically can be generalized to variables. The question is, what does it mean when I make that generalization? Once I understand what that new thing with variables in it means, then I can start looking at specific examples. I'll do that. Come on. Have more questions, ask me more stuff. Is that my wrench problem?
Yeah.
Okay. Then let's, for the moment, let's ignore the wrench itself. And let's just consider the 2 points that we need. We've got this point P down here. And I've written underneath that an ordered pair. I'm going to make my life easy. I'm going to make that point the origin, 0, 0. Now, my question to you is, I've got a radial vector that reaches out to the handle here. Yes? So I've got a radius. That's my vector R. And then you've got a force. And the force is pulled perfectly horizontally, right? I am grabbing this handle and pulling straight. What direction is that? Vector terms. If this is the origin, I have an x and y axis. That's the x direction. So I can make this a vector in the x direction. I can make this a vector whose distance I know and whose angle I can figure out. Because I know it's 1 foot over and 2 foot up. I know the length of that by Pythagoras. I know the angle using a little bit of trig. I have a force, and now I need to do a cross product. But cross product, instead of writing I, J, K, and all of the squares, the cross product can be done this way. Length of R, length of F, sine of theta. So ignore the fact that it's a weird looking handle, and just think of the straight line radius, straight line force, and put those 2 vectors right next to each other. It's kind of hard to see. There it is. I drew another copy of R up there. Right? And then I just have to use a little bit of trig to figure out what the angle is. But I know the angle because it's 1 over and 2 over. And if I can do it at this point, then I can do the same thing if I pull from here. Only now my angle changes. This to me looks like a really weird gear shift lever. Or an emergency brake lever on a rail car. And I don't remember which of the car race Fast and Furious movies it was. But in one of them, instead of using the shift knob at the top, the character is using his hand under the shift knob on the shaft. And by changing where you hold the shifter, you change the amount of force you need to use on the shift lever. This is exactly why. Because by moving that radius, I have to increase my force to get the same torque. If I increase my radius, I decrease the amount of force I need to generate. So the torque here should be larger than the torque here because we kept the force the same and made the radius smaller. Torque is in newtons times meters. It's a very weird unit. And because the US doesn't use the metric system, American torque is in foot-pounds. Pounds of force times feet of radius. You can go to the hardware store and buy torque wrenches that are calibrated in the number of foot-pounds of torque they exert. You know who uses them the most? Auto mechanics. Because to get your lug nuts tight, you have to know how much torque you've exerted. Almost every one of those air hammer guns that they use to spin the lug nuts on has a calibrated force resistance, a calibrated torque end. I'm so glad I never spent too much time working on my car, but this helps. Spark plugs have to be inserted with the right amount of torque because they're ceramic bodies, and if you over torque them, you'll crack the ceramics. I did that on a lawnmower. Had to take it back to the store and say, "Get this thing out of here," because I fucked up. They did. More questions. Ask me more stuff. Okay, then one more weird throwaway for you. Problems 45 and 46 have these weird problem formula common. But these two problems in 12.4 talk about the distance between a surface and a point, or the distance between a line and a point that's not on it. That's the depth of that parallel pipe head. And that's our height calculation. So you'll notice in this one, that's the parallel pipe head divided by the bottom. That's exactly the height. And that's the interplanar distance in a regular crystal. That's your cleavage distance between molecular bonds. Useless crap. I'm never going to see it anywhere. Crack, I cut the diamond perfectly. There's so much neat stuff here. That same distance formula is in statistics, what we use for residual distance, which is where we get the errors in statistics. Not R values, error values, residuals. I've forgotten the letter they use. Epsilon. They use epsilon for residuals. And that's how you do least squares, regression lines. You use a dot cross product and a dot product. Okay. More questions. I got 5 minutes with your names on it, or you can all get out of here early. Your call. I'll see you tomorrow. Have a wonderful afternoon.